Hi everybody. I thought we'd have a further look at the DC load project. I've been having a look at that since the last part that we did on this, and looking at making one or two improvements and solving a few of the issues that has been reported back to me as well. So let me just summarise what we're going to do today. Well, the first thing we're going to have a look at is improve the sharing of the power, the balancing of the power MOSFETs. So I'm going to have another look at that and see whether we can improve that. I'm going to look at solving an issue that was pointed out when it's set at zero current. In fact, when the load was switched off, we had a little bit of leakage current of probably 7 or 8 milliamps still going through the MOSFET. So we're going to try and solve that problem. And then there was also an issue which was pointed out where when the fan switched on, the voltage reading on the display of the DC load started to fluctuate a bit. I think those 2 and 3 have got something to do with the same reasoning as well. We're also going to have a look at improving the calibration, and we're going to add some form of data logging facility on the battery capacity mode, and I'll try and cover that as well today. I've updated the software, so there'll be a new version of software. I think now we're up to software version 35. We're going to build it in its project case again, because we've changed now the front panel because of the 5x4 matrix keypad, and I've taken the opportunity to make another minor change as well. And then I've also been asked a number of times now is what alternative MOSFETs can we use for this project. So I'm going to have a look at that as well. So those are the things that we're going to cover today. So let's get started. Well, let's have a quick look at the changes that I've made to the output section of this DC load around the power MOSFETs. I've just illustrated it here by looking at one of the power MOSFETs and its associated transistor, but equally the same applies to the other three. And if you recall, in each of the source returns of the power MOSFETs we had a resistor, a small value resistor, a 0.1 ohm 3 watt resistor. And what that was doing was giving some form of balancing or power sharing between the four MOSFETs. What I've found is that if we can increase the value of that resistor without affecting the overall performance of the circuit, we can improve that balancing arrangement. So what I've done here is I've increased the value of that 0.1 ohm resistor to a 1 ohm resistor, which means we will now get a bigger voltage drop across that as a particular MOSFET draws more current. And that will give us an improved balancing. And the reason behind that is that each of the 4 power MOSFETs are driven from the same gate drive voltage. So the gate drive voltage of each of the 4 power MOSFETs will be more or less the same. However, as the current flowing through any particular MOSFET increases compared to the other 3, you get more current flowing through and you get a bigger voltage drop across that 1 ohm resistor. And what that tends to do is increase the voltage you see on the source of that MOSFET. So that voltage increases towards the gate voltage, so the gate source voltage effectively reduces, and that in turn would reduce the effective drive, the gate source drive to that MOSFET, and reduce the current flow through it. So it gives some form of balancing. Now we're also using that in conjunction with the little transistor there we had before, the Q6, to also give some additional protection in terms of balancing. But because we now have a higher voltage driving the base of that transistor, we also now need to increase the value of the emitter return resistor, in this case of Q6, from a 47k to a 270k resistor. And it's this little arrangement here, the changes that I've made, that's actually improved the overall power sharing of those 4 MOSFETs. So they all more or less operate hopefully now at equal temperature, and the whole circuit will become a little bit more stable. So to summarise, we made some changes to the 4 resistors there, the 4 source resistors. So R22 to R25 have now been changed to a 1 ohm 5 watt wire wound, and R10, R12, R26 and R32 have been changed from a 47k to a 270k resistor. So there's the changes that we've made on the output stage. Here we now have a view of the printed circuit board where you can clearly see the changes I've made to the output stage there with those 4 power resistors in the source return of the 4 power MOSFETs. Previously we had the 0.1 ohm 3 watt resistors in there, and that's now been replaced with a 1 ohm 5 watt wire wound, You could equally use a 7-watt wire wound, and in fact the PCB is designed to take either type. So that will give us some improved balancing on power sharing of the 4 power MOSFETs, and that will work together with that little transistor that we had, that little protection transistor, the PN2222A, which is just behind these power resistors there. I'll just zoom in and show you that. Right, here we have the closer view of that area there with the power resistors, and just behind there you'll see those 4 resistors there, which are in the emitter return of the PN2222A transistors, and those 4 resistors there have now been changed from a 47k resistor to a 270k resistor. Those 4 resistors there. Right, well, the next thing we're going to do is fix that little issue we have with the leakage current when we have no load, that small leakage current, and also fix the issue where we have the voltage on the display fluctuating when the fan kicks in, and that's caused actually by some grounding problems on the printed circuit board. Now, the one way of solving that is to add some additional grounding, is what we're going to do today, with some heavy gauge copper wire. But what you can do to test the issue is if you connect a voltmeter between the ground pin, the main ground pin there, which is J4 on the PCB, and then you connect the other end of the meter lead to TP5 there, which is next to the U7 op amp. What you'll find is you may read a few millivolts, and that is indicating we have a small ground resistance issue on the PCB. Normally at low currents that's not a problem, but obviously when the fan kicks in you've got more current flowing in certain areas of the PCB, and then that causes this fluctuation you see on the display. It also causes a little bit of problem in terms of the calibration on that leakage current that we mentioned. So what we're going to do to resolve that problem is add the additional grounding and some additional copper wire onto the reverse side of this PCB. So let's have a look at that. Here we now see the additional earthing that I've added on the underside of the printed circuit board, this heavy gauge copper wire, and I simply used some wire I stripped out of some household wiring cable here, took the earthing strip out there. It's around about 14 gauge wire, but any heavy duty copper wire would do for this purpose. So what we've done is we've actually anchored the copper wire there. I've raised it off the print so it's not shorting anything else out, and we've anchored the copper wire in 6 locations. So it goes there, there, that point there, which is the main ground pin on the test pin, that point there, and then the last point is just there, which is actually the earth return path for the 0.1 ohm sense resistor, which is mounted onto the heatsink. So you need to be careful of that one, and we had to bend the copper wire back at an angle going towards the board, but again away from the PCB, just so it's not touching the heatsink. So that gives us the additional earthing, which certainly improves things and improves the overall performance of the DC load. Now, in addition to that, you'll see I've got some more copper there soldered onto the board, and that is strapping the returns of all those 4 power resistors, those 1 ohm resistors, and I'm strapping those all the way back to the current sense resistor, which is the one that's mounted on the heatsink. So that's improving things as well, because although I did put wider tracks here on the printed circuit board on both sides, I still got some voltage drop on the print, and that did affect the overall performance. So by adding this additional copper track here, we're improving things there as well. Well, here we have a slightly different view and closer view of the that additional earthing I've added on the underside of the PCB. You can clearly see now it's raised up from the board itself and anchored in those 6 positions. The only one that is not that obvious from this view is the one there. I'll put my finger behind it, and you can see that one there where I've got slightly thinner wire going from the earthing strip down through the board. It's actually soldered at either side of the PCB, so that goes through a little slot on the board, which is already there. It's a little test point, and it's a through hole, so we just put that straight through and solder from both sides. and I'll show you the position of that when we have a look at the other side of the PCB. I'll just point out the area of the board where we have that earthen wire coming through. It's actually there next to the operational amplifier, that's U7, and you'll see there you've got a little test point labelled TP5, which is plated through a hole to the other side of the PCB. It's a ground point, so all we've done is put a wire through that test point to the other side of the PCB that's then anchored onto that additional copper, and we solder it on both sides of the board. Now I've actually put together a little information sheet just illustrating exactly where you connect the extra copper wire to on the underside of the PCB, and I'll make this available to you as a download, so it'll make it a little bit easier for you to add the wire, and it shows you clearly all the points where the copper is soldered onto the main PCB. And you can also see here it shows you the extra copper we've added to the print there around the source return resistors on the power MOSFETs. So this will be made available to you. Also on this information sheet there is some additional details of exactly where all the connections are made. Now another area of the PCB I'm just going to make a slight improvement on is the area where we connections to the drains of the 4 power MOSFETs and then to the dual Schottky diode there. Remember that we've now got the 4 power MOSFETs bolted to the heatsink with insulating mica washers, so they're no longer using the heatsink to connect the drains of the 4 MOSFETs which we had previously. So we're relying on this track here on the PCB, and although I tried to mitigate the problems of current handling by adding an additional track on the other side of the PCB, it's still probably not sufficient at the higher currents, certainly up at 3 amps. It does seem to work okay up to about 2 amps with no issues, but once you get to the higher current ratings on the load, then the resistance of that track does cause a bit of an effect. So what I'm going to do is just scrape the green coating there on that, the protective coating, off of that copper part of the track and expose the copper, and then I'm going to run some solder on that just to build up the current handling capability of that track, just to improve that. And I'm also going to do the same around the fuse holder there and to the connection where you've got the positive end of the DC load. So let me just go and just clean that up. I'm going to use a little craft knife just to scrape that off, and then I'll just show you what I've done, and then I'll run some solder on that. Here's the actual board itself that I'm using with this is one with the components on, but I've taken off the power MOSFETs for the moment just to do this. And you can see there I've scraped away that coating that was on the copper track there to expose that copper, and also around the fuse there as well. So I'm going to run some solder on that now just to give it some increased current handling capability. Here you can see now how I've run the solder now down those tracks just to give it that extra bit of current handling capabilities. And the only thing you need to be careful of now is that when you're bolting the board itself onto the case, make sure that you've got a space between the edge of the board and the heatsink. So you need to have maybe a millimetre or two space between the edge of that board and the heatsink itself, so that doesn't short across to the heatsink. Now one option you could use just to make sure that the board itself is not touching the heatsink is to use some heat shrink sleeving, so it's heat resistant, and then we can maybe position that on the edge of the board, butt it up between that and the heatsink just to give it some insulation, so there's nothing touching the heatsink itself. So you can either do that or simply just make sure that it's standing off from the heatsink, as I say, either 1 or 2 millimeters. Now I just want to point out a component change I've made on the PCB to improve the setting of the voltage on the display. We had a few minor issues when we were adjusting RV2 to set the correct voltage on the LCD display during calibration, and what I found is that the resistor there, R43, which is providing some negative voltage to back off any erroneous voltage going on to the ADC, that resistor is a little bit too small. in value, and what I found is changing that 270k resistor to a 1 megohm resistor improves the calibration of the voltage setting using RV2. So that's another change that I've made. Another area of the schematic you might want to have a look at yourself and play with is the value of R39. I've put a 1.8 megohm resistor in there, which supplies a negative offset voltage to remove any error voltage which is getting back onto the ADC when we're monitoring the current on the display. And what I found is that the 1.8 megohm resistor works reasonably well across the whole range of currents, and that's what you see on the DC load LCD. There is a slight discrepancy between the lower and the higher current readings of maybe a few milliamps, and if you wanted to play with that resistor, then what you could do, if you wish, you could replace the 1.8 megohm resistor with a 1 megohm resistor, and then you could add in series with that a little variable trimmer, let's say something like another 1 meg trimmer, and then by adjusting that trimmer you can alter the amount of offset we're providing, and you could probably then improve the tracking of the DC current as it's displayed on the LCD. So that's another option you can play with, but for the moment I'm going to settle with the 1.8 megohm resistor. Here we have a view of the other side of the heatsink, and you can see now I've added 2 fans there side by side to give us the additional cooling, and that's simply just bolted onto the heatsink itself and then wired through to the socket on the main PCB. Here we see the changes I've made to the front of the project case. As we're now using the 5x4 matrix keypad, this actually has the load on off facility on there. So what I've done is I've removed that from the front panel. I've put the power on off where the load on off button was previously, and then where the on off button was previously I've now put a BNC socket, which is the trigger input. So we now have the trigger input mounted on the front of the unit. If you were to continue using the 4x4 matrix keypad, you'd have to have the trigger input at the back and go back to the original design where we had the power on off there and we had the load on off just under the rotary encoder. So everything else has remained more or less the same. It's just that we've now got the larger keypad there, and we've got the facility for the trigger input also now on the front panel. Here's a view of the other side of the front panel. I've got all the wiring soldered onto the items on the front panel itself, and they're now ready to go into the main PCB. So all the leads and the sockets are on. For the trigger input, I actually use some thin screen cable, and then I just wired a socket onto that. And then this cable you can see here is going to go to the power input jack on the back of the unit. Here we have a view of the wiring behind the terminals there on the back of the front panel, and how that's wired onto that switch there that can switch the sense input on or off. Now before we mount the printed circuit board and the heatsink into the project case, we just need to raise the front of the PCB to the same height as the rear, where it's clamped effectively to the rear, the heatsink there, by the power transistors. The actual board itself is not bolted to anything at the back. It's really just supported by the legs from the power devices bolted on the heatsink. So if we measure the distance there, we've got around about 35mm from the base of the PCB to the bottom of the heatsink in this case, but your heatsinks may be different to this, so you have to do yours accordingly. And we measure the same distance at the top, so we need to raise that up to, but in this case, about 35mm. And to do that, I'm using some nylon spacers. I've already got 2 of them here bolted onto the printed circuit board with nylon nuts. These are 15mm spacers in this particular instance, and I'm going to use another 4 of these nylon spacers just to raise the front of the PCB up. So we're just simply going to screw them into what's already there. But you can, whatever method you have of fixing it into your project case, obviously it will depend on the type of heatsink that you choose at the end of the day and how high you have the PCB from the bottom of the project case. But in this case we're raising it to about 35mm. So there we are. There we have the standoffs now at the front of the PCB. That'll support the front of the printed circuit board when we mount the whole unit now into the project case. Now for connecting the Arduino Nano serial data to our PC, we're just going to use the standard cable that comes usually with the Nano, which has got a standard USB plug on one end and a mini USB plug on the other end, and that just simply normally just goes into the Arduino Nano there. So that's what we're going to do. And you have two options now, because I want to have the socket in the case that we can then plug into. So what I've found on the internet is you can use one of these adapters which converts a standard USB to a USB-B socket. So it's going from a USB-A socket to a USB-B socket. That will then simply plug in to that short lead, and the idea is that we will have that bolted down inside the case, and then we'll use a standard cable then to connect it from there to the PC. Now the other alternative that we have, which is what I'm going to do today, rather than use the adapter, I'm going to make myself a USB socket cable, and I'm just going to use a USB-B socket and then solder that onto a little matrix board, and then I'm going to solder the wires to that. So what I'm basically going to do is take the lead from the Arduino Nano that you see here, chop off the standard USB plug, and then what you end up with is the wires at the end. You've got 4 wires. Black, red are the power lines, and then you've got green and white is the data lines. Green is data plus and white is data minus. And I'm simply going to solder that onto the USB-B socket, and this is what we have here, and it's just soldered onto that, and then that's going to bolt into the case, and then we've got permanent access from the outside of the case then for logging the data, and also we can use it for programming or reprogramming the Arduino Nano. So that's the underside of the, you can see the connections there. But I'll give you the details of this as a download information sheet. Here we now have a view of the PCB all mounted in the project case with all the front panel leads now connected to the board. You'll also notice down there we've got the USB-B socket giving us access to the serial data out, and that will also be used for programming the Arduino Nano, so we no longer have to take the case off to do that, and I'll simply put a slot in the outside of the case there to give us access to that. Here's another view just looking from this side. Got a better view now of the USB connection there, and also you'll notice I've got a little strip connector there where I'm connecting the 2 fans to, and then a lead from that going to the socket on the main PCB. As far as the DC input jack is concerned for the little power pack to plug into, I think what I may do is mount that, maybe put that in the side of the case there, and then just have a little connection lead. Here we have just a quick look at the side of the project case where I've cut out a slot there for the USB connector, so we've got access to that, and as I say, we can use that both for programming the Arduino and also for logging the data. And then I've just put the DC input jack there, drilled a hole on the side of the case, and then a connector behind that that then goes onto the lead inside that goes to the PCB. So that's the DC jack in. Now for this upgrade today, I've done an upgrade also on the software, so it's now going to be software version 35, and I'll supply a copy of this both for the 4x5 matrix keypad and also for the 4x4 matrix keypad, so you'll have 2 options. Just want to point out what I've changed in the code. At the start of the software where you set all the variables, I've got one there that says the set current calibration factor. I think it was previously set at 1.000. I've now changed that to 0.98. And the reason behind that is that with the improvements that we've made now onto the PCB, with the extra copper that we've added and the grounding, we can also now take a better account of the total resistance of the current sense resistor. Although we're using a 0.1 ohm current sense resistor, you've still got the resistance of the tracks as well, so we need to take that into account. So the effective resistance of the current sense is going to be slightly higher than the 0.1 that R17 is. And that's taken account of with this factor here. So that seems to work quite well. It's also a factor that you can play with yourself. So if you find your DC load is not quite right, you can adjust that current calibration factor slightly up or down. It's something that we can have a further look at later, and may even give an option in the setup procedure. So maybe we can make a code change where you can change that on the DC load itself by using the buttons on the keypad. But for now, I'm setting it in software, as we see here. Now, I've made also some other changes to this software for data logging, but I'll cover that in the other video I'm doing alongside this one, which is going to go through the data logging procedure. Now, I'll give both of these as downloads again, both versions of software for either of the keypad versions you're using, and I'll give that in a link below this video. Well, I now have the DC load wired up to a power supply, so we're going to go through the initial setup for calibration. So I've got a power supply here which at the moment is set at 5 volts, and that's going to the input of the DC load, and I've also got the sense wires going back to the power supply as well, and the sense switch there is switched down to on. So I'm going to switch the unit on. It goes through the intro screens and then should default to the constant current mode, which it has done. And the first thing we're going to do is set the reference voltage. That's the 4.096 volt reference source on the board, and I've got the kettler there, you can see at the back, that's connected to J7, the test pin for that reference voltage, and to ground, which is on J4, and that's the ground pin next to the DC input pin on the PCB. So I'm going to adjust then RV5 until we get a reading of 4.096 volts on the meter there. So let me do that. Take it down slowly. Just about there. So 4.096. Just hovering there between. I'm going to leave it there. So it's 4.09604. So that's near enough. So that's the reference voltage now set. And the next thing I'm going to do is set the 5 volt on the display here to correspond with what we've coming out of the power supply. And you can see the display on the DC load at the moment showing 4.993. So I'm now going to adjust RV2 so we have the same reading on the display of the DC load that you can see on the power supply. So let me just adjust RV2. Take it up, 4.999, so we're just about there. I think that's it, 5.002, so it corresponds now with what we've got on the power supply. Now, one thing you'll notice is that although we've got no current set on the DC load at the moment, we've got some leakage current of around 11 milliamps showing there on the power supply, hovering between 11 and 13. And this is an issue we had previously, and I had a number of comments about this. So what we're going to do now is, with the changes that we've made on the board, with the improved grounding, we should now be able to zero that down to 0, or certainly down to around 1 milliamp. So I'm going to now adjust the current null preset, which is RV3, and get that down to 0, or as close to 0 as possible. Now, if you don't see a leakage current when you've plugged your DC load in, it could be that your preset is wound to the other end, so you wind it back until you see a leakage current and then you back it down again. So I'm now going to adjust RV3, and we're going to
try and get the current you see there on the power supply, the leakage current, to go down to 0. And do this very slowly, because if you take it too far it just upsets the whole calibration. So the trick really is to get it as close to 0 as possible without going past once you get to 0. So it's just about there now. There we go. And once you get to 0, stop, don't go any further. If you're not sure, just back it back off a bit to 1 and then just tweak it slightly. So that's now set to 0, we've got no leakage current. And just to double check now, this is with the load off, so let's just switch the load on and make sure that the leakage current is still 0, which it is. And the next thing we're going to do now is set the current calibration preset, which is RV4. So let me just switch the load off a minute. And I'm going to set the current to 3 amps and then enter that. And then I'm now going to switch the load on. And you can see there now we've got 3 amps load, but if you look, we're only drawing 2.955 there, shown there on the power supply. So I'm now going to adjust RV4 until we get 3 amps. So just keep an eye on the power supply there, the current showing. Take it up. Too far. It's just about 3 amps, just slightly over 3 amps there on the power supply. 3.003, and on the DC load it's showing 3.009. So a slight discrepancy on the DC load, but there is it's within probably tolerance, and I'm not sure how accurate the power supply current reading there is anyway. So I'm happy with that. We're going to leave that there, and what I'm going to do now is just step it down to 2 amps and just see if it tracks. So yeah, it's 2.002, and on the DC load it's 2.005. Go down to 1 amp, and it's 1.001, and it's 1.001 on the power supply there. So that seems to be working quite well. So that's the initial calibration setup. Now what you should do, because the DC load hasn't been operating and the MOSFETs are quite cool, so I'm going to set it to 1 amp at the moment, and I'm going to step the voltage up to 30 volts. So let me do that. So we've got 30 volts there now, and you can see there on the DC load it's registering as 30.17 volt. We've got the current set to 1 amp, the load is on, and we're drawing 1 amp, and it's showing 0.998 milliamps there on the power supply. So if you leave it like that until the temperature goes up, what we want to do is allow the temperature to rise so the MOSFETs are just warming up, and then just go through the final calibration again for RV4. So I've had the unit now running for about 5 minutes or more, just warming it. When you see the temperature now is at 35 degrees C, we set to 1 amp still, and you've noticed there, you see how on the power supply it's dropped down to 0.996 milliamps, 994. So what we're going to do now is, because it's heated up, the MOSFETs are warm, I'm going to set the current to 3 amp. So the load is still on, so I'm going to do it with the rotary encoder and turn it up now to 3 amp at 30 volts, and then I'm going to adjust the preset RV4 until we get a reading of 3 amps there on the power supply. So let me just adjust that. Turning up RV4. Too far. So we can get it round about 3 amps. It's just about there. It's 3.003, and on the DC load, it's showing us 3.019, so it's a slight difference on the DC loads, but we're drawing 3 amps now at 30 volts, so that's just over, we've got slightly over 91 watts there of power running at the moment. And you see the temperature's shot up now to 42. Now I've got this set in software, so when it reaches 40 degrees C the fans turn on. And one of the issues we had previously, when the fans came on, we had a slight fluctuation in the voltage reading. You can see now that's rock steady now, so we're not getting that problem that we had previously. And that's because we improved the grounding with those wire straps that we put on the underside of the PCB. So that seems to be running quite well now at 3 amps. And I've got both fans are now running at the moment, and the temperature will go up a little bit more probably, but it's looking as though it's working quite nicely. Now I'm just going to take it up to 4 amps, which is the limit I've set it to at the moment. I've exceeded the power because we had the power limit set. So what I'll do, I'll go back in and I'll change the power limit just so we can test it at 4 amps. So let me reset to constant current. Now I've just gone into the limits setting and I've set the current to 4 amp. I've set the power limit now to 150 watts and the temperature limit to 60 degrees C. So let me just enter that. Right, so what we can do now is if we now set the current now to 4 amps again at 30 volts and turn the load on. So we're now drawing 4 amps, 120, well just slightly over 120 watts at the moment, and you can see, although we've got here on the DC load, it's showing 4.036 of an amp. On the power supply it's showing us 4.016. So just a slight difference there. But it seems to be handling 4 amps, 120 watts, just over 120 watts. Temperature obviously going up. The fans have now kicked in at 40 degrees. I've got 2 fans, remember, on the back, and the voltage is nice and constant on the display.
We'll just take a quick look at the 4 MOSFETs there in terms of how they're heating up, and I think you can see from the thermal camera that they're heating up fairly evenly. Now I've had many questions about is there an alternative power MOSFET we can use for this DC load project. So what I've done here for you is I've done a little bit of research and just put a little summary sheet together for you of possible alternatives to using the BUK 956R1 MOSFET. And I'm just comparing them here, some of the main features of the MOSFET, so you can see how they compare with the one I'm currently using. I've put them in the order of preference, so obviously I still prefer, if you can get it, to use the BUK 956R1, but then in order of preference below that I'm giving you some alternatives, and a nice alternative is the ST Microelectronics one, which is the STP80NF55L. Although it's a lower drain source voltage, so you wouldn't be able to use it higher than say around 50 volts, it gives you similar power rating. It operates at the same gate source threshold levels, and in fact its power derating factor is a little bit better than the one I'm currently using. So that is a nice equivalent if you can't get hold of the BUK 956. Below that we have a few other power MOSFETs, one there by Fairchild, another one by ST Microelectronics, and then one by IR, International Rectifier. And it's actually those 1, 2, 3, 4, 5, the first 5 power MOSFETs on this list are the preferred ones, and then you have some less obvious ones there from Infineon, and although you can use them on this project, you wouldn't be able to use it to the same power rating as you can
the ones I'm suggesting higher up this list. So there we are. There have some alternatives. So if you find it difficult to get hold of the BUK 956, then have a look at getting them in the order of the preferences I've put down here. On the same information sheet I'm giving you with the alternative or possible alternatives of power MOSFETs for this project, I'm also showing you the safe operating area graph for the first three on the list. And I'm comparing the BUK 95R1 with the ST Microelectronics STP80NA55L, and then looking at the Fairchild RFP12N10L. So just comparing the first three I've got on my list there. And you can see I've indicated each of them in the 30 volt 3 amp level. That's 90 watts effectively. And you can see all three of them can more or less handle that. But bear in mind that the safe operating area of these power MOSFETs shown on these graphs relies on the fact that this is at 25 degrees centigrade. Now in reality, once you start drawing current through the power MOSFETs, it gets hotter, and as the power MOSFET gets hotter, that power rating will drop. So if we take the example of the BUK 956R1, which shows you at 25 degrees C, it can give us 30 volts at 3 amp, that's 90 watts. But as that heats up, as we draw more current through it, that power rating of 90 watts will drop. And you'll see on the information sheet I'm going to give you as a download, there is a power derating factor above 25 degrees, which indicates how many watts or fraction of a watt it will reduce for every degree above 25 degrees centigrade. So you have to derate that level, and in reality what you'll find is that when they're operating normally and they're getting hot, instead of getting 90 watts possible from the MOSFET, we probably get somewhere nearer 40 or 50 watts. But because we're using 4 power MOSFETs in our project, then we've got some power sharing, so we're able to go up to around about 200 watts maximum in this particular project. Well, I think I'm going to leave the project there for today. It's going on a little bit longer than I thought. So with regard to the data logging software and procedure, what I will do is do a quick little video, separate one for that, and I'll upload that as well, so you'll have all the information on how to do that. But for the time being, I'm going to leave it here. I hope you found the upgrade of interest. What I will do as normal is give you all the links down below for all the latest documentation for this and the updated schematic. And if I do make any further changes, obviously I'll keep you advised. But in the meantime, I'm going to say cheerio, and if you found this of interest and helpful, please give me the usual thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.